Hello everyone, welcome to the 34th lecture in the series. In this lecture, we are going to study about the algorithmic approach called as divide and conquer. We will be first seeing what this divide and conquer approach is. Then we will see the classical example for divide and conquer approach with merge sort with this particular lecture. First, let us see what divide and conquer approach is. So, it is an algorithm design paradigm. So, it includes three sub-steps. The first step is divide. So, given an input data and if we want to do something with that input data or solve some problem with those data, we will be dividing the data into disjoint subsets. So, if in case we consider the data to be yes, then we will be dividing the input data into one or more disjoint subsets S1, S2 and up to Sn. We will then proceed to the next sub-step, which is conquer step, where we make an attempt to solve each of those sub-problems recursively. And in the combine step, which is the last step of divide and conquer approach, where we will be combining the solutions of each of our sub-problems, namely S1, S2 up to Sn, in order to find the collective solution for the particular data set S. So, this divide and conquer approach will have a base case for the problem, and then the rest of the steps in that problem can be solved by following the recursive steps. And this in order, since it involves recursion, we can do analysis for such problems that involve recursion with the help of recurrence equations. So, we will be seeing how to do that analysis with recurrence equations. So, when it comes to divide and conquer approach, we say that it is meant for designing fast algorithms in sequential computation. Not only that, divide and conquer approach finds application even in the field of parallel computing. So, whenever we have some large complex problem, we do not try to achieve it, solve it in a sequential fashion. We, with respect to parallel computing, what we do is that whenever we have a large complex problem, we divide it into smaller sub problems, and we can use approaches to solve each of those sub problems separately, compute solution for it, and finally we will be merging all the results of sub problems to find the solution to the bigger problem or the large and complex problem that we have taken initially. So, that is what we imply here. We have a large problem, we have broken down the same into several sub problems, we solve it independently and finally merge up the results. So, as a classical example for this divide and conquer approach, with this particular lecture we are going to study about merge sort. So, in the next lecture we will be studying one more example that adopts this divide and conquer approach, which would be quick sort. So, as such, this merge sort is an algorithm which is meant for sorting the set of input. So, you are given with a set of input elements and those elements are out of order, and this algorithm helps us to put that input data back into some order. So, we are using this merge sort probably to sort elements that are more in number, right. So, that is when we can realize the purpose of merge sort. So, for this particular sorting algorithm, we have an input sequence S, and that sequence contains n number of elements, and we are going to adopt those three steps that are part of divide and conquer approach. First, we will be dividing that sequence into n number of subsets, and we will be conquering it, which means we will be recursively sorting each of the sub problems or subsets, that is S1, S2 up to Sn, and finally we will be merging that results. So, for simplicity sake, what I have shown is that we are dividing the sequence into two subsets S1 and S2, where each of those subset contains exactly n by 2 elements, and we will be recursively sorting each of these two partitions, and finally we will be merging S1 and S2 in order to get the sorted sequence. So, this should be the algorithm for merge sort. We are given with the sequence of length n, and we have a comparator operator which is C, and output should be the same sequence S, but it should be sorted. So, first we check whether the sequence size is greater than 1. Only if it is greater, then we will be partitioning that sequence into 2, which is S1 and S2, and each of these S1 and S2 contains exactly n by 2 elements. And finally, as a next step, we proceed to the conquer step, where we do we repeatedly call this merge sort. So, as such, the sequence, I mean this partition is going to invoked recursively, and we are going to break it into 2 again and again. So, this partition S1 will be repeatedly divided into 2, and likewise the other partition S2 will also be repeatedly chopped down into size of 2, right. And we will be applying or solving each of those subpartitions first, and finally we will be merge each of those subpartitions in order to get the final output, which is S, which is sorted by this time. So, these are the steps that we adopt with merge sort. First, we have an array of size n. So, the index spans from 0 to n minus 1. We will be splitting this array into 2 equal halves and make copies of each of those half in arrays B and C. So, here in this case we are creating auxiliary arrays which are B and C. So, these auxiliary arrays will be sorted recursively, and finally we will be merging those two arrays into the original array A. So, for merging we adopt these steps, that is, we will be repeating until no elements remain in any one of those auxiliary arrays. So, we have two auxiliary arrays B and C. We will compare the first elements in B and C, and we check which among these is smaller, and the one that is smaller would be copied first into the array A. So, then after copying we will be incrementing the index by 1, so that we move to the some other unprocessed position of that array. So, this step gets repeated until all the elements from B and C are moved to the original array A. So, once all the elements in the arrays are processed, at times there is a possibility that array, say the auxiliary arrays, one of those auxiliary arrays have become empty. If in case once all the elements of one of those auxiliary arrays are processed, then the remaining portion of the unprocessed arrays can be copied up from the other auxiliary array. So, we will see this with an example, then you will be better understanding how merge sort actually works. So, this is the pseudocode for doing the merge sort. So, you are given with an array A, this is what we want to sort, and the array has such contains n number of elements, and those elements are out of order initially. The output that we expect from merge sort is we have the same array, but now the elements are all sorted. So, we check whether the size of the array is greater than 1. If so, we copy the first half of the array's elements into the auxiliary array B, and the second half of this array A into another auxiliary array C, and then we will be recursively sorting the elements of this array B and recursively sorting the elements of array C, and finally we merge the arrays B and C onto A, so that as a resultant we will be having only the array A, while B and C would have become empty. And this is the pseudocode for the merge step which we do with this particular merge sort algorithm. As such, during the initial divide phase, we will be keeping on dividing the array into subpartitions, and once we have reached the smallest partition size of 2 or 1, then we could no more do any kind of partition there, and by the time we will be actually doing this merge step. So, while we have broken down it into subpartitions, there we even do make use of this comparison operator to put all the elements in that particular subpartition in sorted form, and finally we will be merging those sub partitions to get the final result. So here we make use of three variables I, j and k, and you could see here that the auxiliary arrays B and C have their sizes P and Q. So we want to merge them finally to get the original array A back, right. And so P marks the end of the first array, which is B, and Q marks the end of the other auxiliary array, which is C. As such, I, j and k are initialized with values 0. So what we do is that we will be repeating this process till we reach the end of the first array, that is B, and the end of the other auxiliary array C, which is Q, right. And so we check whether I is less than P and j is less than Q. So every time what we do with every subpartition is that we check the element at index I with the element at index j of C, that is the first two elements in the respective partitions. If B of I, that is the element at this auxiliary array B, first position in this auxiliary array B is less than the first element of this auxiliary array C, then naturally the first element from B would take up the position in the original array A. It is the smallest, and so it occupies the position denoted by k, and after that we increment the value of I by 1. If not, if in case the first element of the auxiliary array B is greater than that in C, in that case the element from C would occupy the position k in the original array A, and we would increment j by 1. So whatever be the case, whether I incremented or j incremented, as such we have moved an element from either the auxiliary array C or B onto array A, and array A's index is k, and so after this movement we have to increment k by 1. So if in case we have reached I is equal to P, it means we have reached the end of the first auxiliary array. In that case, what we have to do next is that we may have some elements still left with the auxiliary array C, and all those elements are already in sorted order, and so they can be straight away copied back to the original array A. If in case otherwise, that is we have reached the end of the second auxiliary array C, in that case what we would do is that all the elements from the auxiliary array B, the rest of the elements from the auxiliary array B could be copied away straight away into the array A, right. So this is how your merge phase works. We will see this with an example, then probably you will understand it better. So your merge sort algorithm takes as input original array A and two other inputs, which are nothing but the starting and the end position of the sub problem. Say for instance, if you have considered a partition, so here P marks the beginning of the partition and R denotes the end of the partition. So those two are the other two arguments. So every time what you do is that given a partition that is greater than 1, we are supposed to break down it into 2. That is what we call it as the divide phase. The initial checking that we do, that is for checking the base case. So if it is less than 1, then it falls under the base case. If it is greater, then we use this divide and conquer approach. And now we have broken down this particular partition into 2, so that we will have one partition spanning from P to Q and other partition spanning from Q plus 1 to R. So we do merge sort separately on each of those subpartitions, and finally we will be merging up results back into the original array. So initially during the first run, we will make a initial call to this merge sort algorithm with these three as input, that is we will give the original array its start position and its end position. So now we will see with an example what would happen or how this merge sort would work when the array size is a power of 2. Let us consider that we have this as the input, that is an array containing 8 elements, right. So 2 cube is 8, so we say that it is power of 2. So now in that case the array index, you could see that it starts from 1 and ends up in 8. So we will find the mid, which is the value for mid is put up in the variable q. So the value of q would be 4 in this case. So since it is 4, the first 4 elements would be one partition and the other 4 elements would be other partition. So P to Q would be 1. So P was 1, q was 4, so 1 to 4 would be one partition. Q plus 1 to r is 8 in our case, and so 5 to 8 would be the other partition. Now we may have to do this merge sort on this particular sub problem. So as such, since it has 4 elements, it would again be broken down into 2 sets of 2 elements. Likewise, we do for the other partition too. It contains 4 elements, and so it is also broken down into 2 subsets of 2 elements each. And then we think of dividing it further. So when you divide it further, this partition contains only 2 elements, and so they would be just treated as 2 separate elements. Likewise, we do for the other partitions as well. And finally, what we do is that we will be doing comparison here. We check whether 2 is greater than 5 or less than 5. In our case, it is less, and so 2 should come before 5, right? And when we compare 4 and 7, 4 is less, and so 4 occupies first. Likewise, we will be solving these sub problems separately and finally merging the results. So now we see how this conquer and merge phase works. So as such, with the previous slide, we have seen how we ended up with divide. So we have split this elements into separately, right? So this original array of size 8 is now decomposed into 8 separate elements. For conquer and merge phase, what we do is that for conquering step, we will be checking the first 2 elements. As I said, since 2 is less, we move 2 first and 5 next. Likewise, we do that kind of revision over each of these sub problems here. 1 and 3, they are in order, and so as such 2 and 6, they are in order, so they are left as such. So here, except that the first set, all other things are already in order, so we need not do anything over here. And then we proceed with merging these 2 sub partitions 2 5 and 4 7 to get this 2 4 5 7. So you could see that whenever we do a merge, we always ensure that the elements are putting up in order in the merged list. So we take up the first element from this partition and the first element from this partition. We compare them. Among this, 2 is small, so 2 is occupying the first position here. And after that, we will be moving to the next position to denote who should occupy this position. So now for this case, we have to compare 5 with 4 and 5 with 7. So in that case, this is already in order. So we will compare 5 and 4, and among this 4 is less, and so 4 has occupied this position. And then we are supposed to compare 5 and 7. As 5 is less, this 5 has moved to this position. By the time your left partition is already empty, this auxiliary array, in our case this is our B has become empty. So now we are left with only one element in C, and that is straight away copied to the 4th position. So this is how every merge step works, a conquer and merge step works. Likewise, we do for the other half, and finally we merge up all the results, and you could see that the entire set of elements are now in order. And one more thing to be noted here is that we have a particular situation where here the first element is 2 and the next partition the first element is 1. So we have put up 1 in this place, and during the second iteration what we will have is that we may have to compare the element at the first position in the auxiliary array B with the element at second position at the auxiliary array C. Now you could see that both the elements have the same value, so one among this would occupy the next position, and followed by that we will make a comparison of 4 and 2, and finally this 2 would have occupied this position. So you could see that when the values are same, their relative ordering is not disturbed, right? We are actually having 2 2's following each other, and so we say that merge sort is a stable algorithm just because it preserves the order of the elements even when 2 elements in the subpartitions are one and the same. So we will see one more example where your n is not a power of 2. So here you could see that the number of elements in this particular array is 11, and so when we move to the divide step, then your divide step should work as 1 plus 11 by 2, where q would have a value of 6, and so elements from 1 to 6 would be one partition, and elements from 7 to 11 would be in the other partition. So, as such you could see that the number of elements here is even and the number of elements here is odd. So, that is the case when we have n which is not a power of 2. Both the partitions would not be of the same size, where one would be bigger than the other. So, as such, since it has 6 elements, you could have broken down it into 2 subsets of size 3, whereas here just because this partition has only 5 elements, we would be ended up with one partition having 3 elements and another having 2. And after that we have to break down this sub partition of size 3 into 2, and as such we will be having as 2 and 1. Likewise, this will also have 2 and 1, this will have 2 and 1 element, and just because this partition has only 2 elements, we are separating it out as 2 separate elements. And in the last divide phase, you could see that with the last subpartition we are not doing anything, just because it is already separated out, while all other things they had 2 elements each, and so they are separated down into single element, right. And the next step phase is conquer and merge phase. As I said before, we will be looking at the elements 4 and 7, they are in order, so they are taken as such. 6 and 1, they are out of order, so they are put in order. 7 and 3, they are out of order, so they are put in order in this step. And then we proceed with merging at this level. So, at this level while we merge, we check whether the first element here and the first element there, we compare them, and the smallest of them would occupy the first position. Likewise, we will be repeating for every subpartitions that we see here, and finally we merge up all the results to get the final sorted array. So, thing to be noted here is that we keep on dividing till the partition is left with 2 single elements during the divide phase, and then we keep on merging them until those partitions, or I mean we reach up to the final array, that is the auxiliary arrays would become empty. And while we doing so, we actually do a comparison step and see that each of those subpartitions actually hold the elements in sorted order. So, this is how your merging actually works. We have the input array, we have 3 indices P, Q and R, where P denotes the start and R denotes the end, and Q is some mid position within your array. So, what we do first is that we ensure that the elements from P to Q are sorted, then we ensure that the elements from Q to R are all sorted, and finally we will merge up all those 2 subpartitions to get the single sorted array, which is our A. So, this is our idea for merging. Imagine that we have 2 piles of sorted cards, and then we will be doing or choosing the smallest of those 2 piles, and that would occupy the first position, right. So, we will be removing the smallest from the pile and put it up in the output pile. So, we will be repeating this process until the piles become empty and all the elements from each of those piles have been moved up to the output pile. So, that is the principle which we adopt for merging. Of course, we have learned this already with an example. So, for simplicity's sake, I have shown you one subpartition, and we will be checking how it actually works with this subpartition. So, we are focusing our attention to one portion of an array where the starting index is 9, the ending index is 16, and the middle position, that is Q, is 12, right. So, this was the initial positioning of those elements. Now, we have broken down it into left and right, or auxiliary arrays B and C, right. And you could see that the left partition contains 4 elements and the right partition also contains 4 elements, and the index spans from 1 to 4 here and 1 to 4 there. So, these 2 are the auxiliary arrays, and for I mean navigating through the first auxiliary array we use the index I, and for the other we use the variable j. Now, we have to fix up which among these should occupy the first position in your array. In our case, we are considering one subsegment or partition whose starting location is 9. So, we decide which element should occupy the position of 9 here. So, we compare element at index I with element at index j. As such, the element at index j is less, and so this element is moved from this pile to the output pile. So, A is our output pile in our case, and after this movement j should be shifted by or incremented by 1, and we have the variable k to mark up this index, and k should also be incremented to the other position or the immediate next position. So, now we have to decide which among the remaining 7 elements should be brought up here. So, for doing so, still I is in its first place, but j has been moved to the second place. So, we need to compare 2 with 2. So, they are equal. So, we assume that the element from the array L has been moved up to this place, and I had been incremented to the next position, right. And so, j as such, it is pointing to the second element in this auxiliary array. So, that is the state which we have shown here. So, during the next iteration, we assume that we have moved up the element 2 from the auxiliary array L into the 10th position, and so we have stricken it off. And by this time, you could see that one element from each of these auxiliary arrays have been stricken off, and they have been moved to the output pile. And during the next iteration, what happens is that the other 2 should be moved to the place of 11 in the output pile, and so it has been moved, and it should also be stricken off. So, at this point of time, the left auxiliary array contains 3 elements with it, and right auxiliary array has 2 elements with it, which have to be moved to the output pile. Now, we compare the elements. You could see that elements till position 14 have been moved up, which means the elements 4 and 5 have been moved up here, and we have left up with one element in each of these piles. And at this particular juncture, you could see among 6 and 7, 6 is less, and so it should occupy the position 15, and this is how your state after moving 6 from this output pile. So, by the time we move 6 out of this pile, then what happens is that the right auxiliary array has completely become empty, and so we have only one element left in the left auxiliary array, and since we do not have anything to compare with the other partition, we can straight away move this 7 to the output pile. So, that should be the last step here, and finally, at the end of this, all the elements from both the auxiliary arrays have been moved up, and we say that we are done with this process. So, this is how your conquer and merge step works, and finally, we get one array which is sorted, the original array that is sorted. So, when you look at the running time of this merging process, so initially we spend some time on copying the elements from the original array to the auxiliary array. So, we assume that we had 2 arrays, and so we did copying twice, and so it is going to be order of n. And then we add the elements to the final array. So, that is movement of elements from auxiliary array to original array, and that may even take up order of n, and this merging step would also take time of order of n. So, when we generally do analysis of this divide and conquer algorithms, since it involves recursion, we may have to express it in terms of a recurrence relation. So, we will be having a base case and another recursive step. Let us assume that the problem size is n, and so the running time of the problem should be t of n. As such, it is we are using divide and conquer as the algorithmic strategy, and so your problem is divided into a number of sub problems, and each of those sub problems have to operate on data of size n by b. So, for this division step, we will be taking a time of d of n, and then we may have to conquer or solve each of those sub problems. So, the time for solving each of the sub problem is t of n by b, where n by b is the size, and we have a number of such sub problems. So, the total time for conquering would be a into t of n by b. And finally, after conquering step, we may have to combine all those results of the sub problems into one, and that may take up a time of C of n. So, as such, when we put up to all these things together in one equation for running time as T of n, then we could have the base case as when n is less than C, then it is going to take up a constant time of order of 1. Otherwise, it is going to take up A into T of n by B for each of those concurring step, plus some time for divisive step and some time for combining step. So, all these together have to be summed up. So, when we look at the running time of this merge sort, we are computing the average, that is the midpoint every time for the partition, right, which is q, and we take the size, I mean p plus r by 2 is what we do. So, for the division step you take a constant amount of time, so it is order of 1, and for concur step, as you know, we will be recursively solving two sub problems, and each of those sub problems will be of size n by 2. So, it should be 2 times T of n by 2. So, we have already seen with an example that every time we keep on dividing it by 2, right. So, it is 2 into T of n by 2, and the last step is a combined step. So, if it is merging of two n element subarrays, then that should take up order of n time. So, your C of n should be order of n. So, now the running time for this merge sort algorithm could then be expressed using recurrence relation as the base step taking up order of 1 when n is 1, and when n is greater than 1, it takes up a time of 2 into T of n by 2 plus order of n. So, to summarize what we have seen so far, we have seen what divide and conquer approach is. This divide and conquer approach should be used when the problem is large, and with divide and conquer what we mean is that a bigger problem is broken down into several smaller sub problems, and that is what we mean as the divide step. The next step is conquer step, where we try to solve each of those sub problems recursively, handling base cases directly, and as a last stage in the divide and conquer approach, we have the combine step that combines the solutions from all the sub problems to form the final solution. And this divide and conquer approach is used by many algorithms which are claimed to be efficient, and one among them is merge sort. And of course, with the next lecture we will be learning about how to perform a quick sort using this divide and conquer algorithmic strategy. Not only that, we have learnt about binary search in detail in one of the earlier lectures, and by the time I taught you binary search, I told you that it also relies on the concept of divide and conquer. And this divide and conquer approach actually helps us to achieve a lower time complexity than other approaches, and for most of the sorting problems, when we use this divide and conquer approach, it is going to take us a time of order of n into log n. And this merge sort in specific, it uses divide and conquer algorithm, and the original array is split into two halves, and we will be recursively solving each of the sub partitions, and finally we merge them up to build the fully sorted array. And it also relies on the divide and conquer approach, and so it should use the same steps like divide, conquer and combine. And when you look at the time complexity of this merge sort, it is always consistent, and so for it the best, average and worst case is always order of n into log n. So, irrespective of the size of input, it is going to perform the same way, and it is claimed to have a consistent time complexity. And now let us see some of the conceptual questions to understand whatever we have learnt so far. And what is the core principle behind merge sort? It relies on divide and conquer, where we have a divisive step that divides the algorithm into two sub problems, keep on dividing the original array into 2, and then it has a conquer step where we recursively conquer and find a solution for the sub problem, and finally merge up the results. And next question is, why is a merge sort considered as a stable sorting algorithm? I told you with an example that if in case a particular element is getting repeated in your array, and by the time we do the merge step, always the relative positioning of elements with same values should be preserved, and merge sort very well handles this, and so we say that merge sort is the best example for a stable sorting algorithm. And what is the time complexity of merge sort in all cases? I hope with the previous slide we saw that it is order of n into log n, irrespective of the size of input. And this is one algorithm which speciality is that it has the same complexity for best, average and worst cases. And the next question is, how does the merge sort differ from quick sort in terms of space usage? We have not seen quick sort yet. So one thing which I can tell you is that with merge sort we have made use of some auxiliary arrays for sorting purposes, and that takes up additional space, whereas with quick sort it relies on in place sorting. We don't create any auxiliary arrays for doing that sorting purposes, and so that is one of the drawbacks of merge sort over quick sort. And then the next question is, can a merge sort be used on linked list efficiently? Why or why not? Yes, we can make use of implementing merge sort. We can use linked list as the data structure, and that is definitely efficient because we actually can rely on pointers and do shifting of elements, and so we say that linked lists are best paired for are best suited for implementing a merge sort. Hope you would have understood the concepts of divide and conquer and the classical example of merge sort.